All right. So out on the street, in this room, there is always particulate present. Dust. Out on the street, there's soot, there's rubber particles from car tires, there's asbestos from demolition, there's silica from people breaking up the sidewalk, and so on and so forth. There's always particulate material there. If you're out in the country, beautiful, clean air, full of pollen, full of dirt particles. If you're at the beach, breathing that nice fresh air at the beach, full of silica, fortunately particles that are probably non-respirable, big particles, full of salt, mold, all sorts of bacteria, and so on and so forth. Always particles around us. Only place you won't find particles in the environment is, say, in a clean room, for instance, where they manufacture these microelectronics, these stuff like that. Or perhaps you have a clean room where they assemble satellites or something like that to make sure that the satellites don't have any particulate material that gets into it that might interfere with their operation, right? So an environment with no particles, pretty much an artificial environment. So there's all these particles around. As far as workers are concerned, we're usually concerned about that specific region or room or area where that person is likely working. Okay, so I'm going to kind of just sketch out a kind of area. Here's a worker, skinny worker, right? His skinny worker working in this space, and this space is, because of his work activities, he's generating a lot of particulate matter in here. Might be large particles, might be, don't laugh at the drawing. That might be large particles, small particles, and so on and so forth. But it could be toxic particles, could be lead dust, could be silica, if he's doing grinding and stuff like that. For our purposes, the version of this particulate measuring, and the techniques are very similar for any kind of particulates. The ones that we're looking at is NOS, not otherwise specified or not otherwise regulated. That's NIOSH procedure 0500. That's total particulates that are not otherwise regulated. In other words, it's not for lead, it's not for sand, it's not for silica, it's not for any pollen. It's just, in general, just what we used to call nuisance dust, right? So, and we know that from the OSHA 500 that the PEL is 15 milligrams per meter cubed. Notice, unlike the asbestos, we're not counting particles, we're counting the weight of particles, right? It's a gravimetric analysis, right? So we want to know what's the concentration of these particles in the space where he's working. Well, the way that we do that, of course, is we set up a pump, we put it on the worker, we calibrate it before and after, we put a cassette with a filter in it, that 5-micron PVC cassette, we put that filter in there, and we run that pump during his 8-hour workday, and we collect that cassette afterwards. We simulated a situation where we would do area monitoring. We just set it up and let it run in an area and see what happens, right? So we have two things we're learning here. We're learning how much material we captured, the weight of dust we captured, and also how much air we sampled. Well, we usually want to know, when we do a measurement like this, we want to know a concentration. In order to know a concentration, we need some kind of standard. Like, in other words, how much? How are we going to define what this concentration is? Well, typically, for this kind of measurement, we're looking for the amount, and even other measurements, we're going to talk about VOCs tonight, even other measurements, we're talking about the amount per meter cubed, right? Meter cubed, the cubic meter of air is 1 meter by 1 meter by 1 meter is a meter cubed, of course, right? So that does, that area, probably we're talking about sampling, the air is moving around and so on and so forth. We're looking at that as representative of this space or the worker's breathing zone. Just as an aside, how many centimeters in a meter? Centimeter means 100, right? There's 100 centimeters in a meter. So instead of 1 meter, I'm going to put 100 here, 100 here, and 100 here. So the area of, you could call this 1 cubic meter, but you could also call it 100 times 100 times 100. That turns out to be 1,000,000 cubic centimeters, right? cc's or mLs, whatever. How many cc's are there in a liter? 1,000, right? So we'll divide by 1,000. So there's 1,000 liters in a cubic meter. Those two are equivalent. If ever comes up, this kind of a handy guide as we go through this thing and we're converting back and forth. That's going to come in handy, I think, at some point. So now let's say we run our pump at 2 liters per minute, and we run it for 2 hours. How much air have we sampled? Well, we ran it for we ran 2 liters per minute for 2 hours, which is 120 minutes. That's liters per minute times minutes, right? Minutes going to drop away. It's going to be 240 liters, right? That's the volume, the total volume of air. Well, okay, now we measure ourselves, or we send out our sample to a laboratory, and the laboratory calls us back or sends us a report, and it says you had 1.5 milligrams of dust on that filter. That's how much the weight increased on that filter. Okay, well, that's interesting. But what am I going to do here? 1.5 milligrams, 240 liters. But the standard is how much per cubic meter, right? Not, and so on and so forth, or in other words, per thing, which is the same thing as 1,000 liters. So let me think about this. If there was 1.5 milligrams, that's the difference between the starting weight and the ending weight, per 240 liters. Well, what's that ratio if I had taken 1,000 liters, a cubic meter, if I actually ran it and found 1,000 liters? How many milligrams would I have found in 1,000 liters? So you can set up this equivalence. This ratio is the same as this ratio, and you can cross multiply. 240x is equal to 1,500. 1,500. Divide by 240. Divide by 240. And x is going to be equal to, it looks like about 6, right? Roughly 6 point, so maybe 6.1. 6.1 milligrams per 1,000 liters, or in other words, meter cubed. That's the calculation. That's it. That's the whole deal, right? So let me just get to that sheet. Okay, and let's see, particular data sheet. Okay, here's our data sheet. I opened it again. Fill in your team members' names, the date and location you took the sample, the pump ID. If you don't have the pump ID, communicate with your other team members, or if you post to the discussions forum, I'm sure somebody will give you that information as well. Sampling meter. What's sampling meter? Where are you going to get sampling meter if you don't remember? You got a copy of the NIOSH procedure. Tells you what kind of filter it was, right? Media type. Contaminant, what are we looking for? We're looking for nuisance dust, of course. Okay, now, here's the weight, and I think I had recommended, some of you have your group established a starting and an ending weight that you were going to use, but some of you did not, right? For those of you that did not, I gave you a proposed, I think a starting weight of 10.000, before, and 10.150 afterwards, and you could use that, right? If you want. So if you want to, you can use that or your own. I will read them all, and I'll make sure that I check the calculation for each one of them. I won't assume that it should have been the one I gave you. Okay, and then we also remember for asbestos sampling, almost any kind of sampling, we always want to make sure we haven't inadvertently contaminated our sampling devices, our filters, and so on and so forth, cassettes. And we also want to make sure the cassettes themselves or the devices didn't have some sort of problem, right? In other words, they weren't contaminated before we even got them. So what do? We take the cassette with the filter in it, we open it up, we connect it, we unconnect it, we don't run any air through it. And then at the end, we pick it up just like we had done before. We open it, take the filter out, reweigh the filter. We do everything we did to the sample cassette, we do to the blank, and we do it exactly the same way, except we don't use it actually filter any air through. So if there's anything we did in handling this thing, or if there's any defect in the material we're using or the filter we were using, we'll see a difference in the weight before and after. So we'll be able to catch, oh, gee, we made a mistake. Not only that, if it's just a small difference, we might even be able, that we can't avoid. We're in an environment where we have to handle these cassettes, and it's a dusty environment. so it's going to get contaminated slightly anyway. We can get the weight before and after, and we can take the tiny amount that that blank had increased in weight, and we could subtract that from the amount of weight that we had on the sample so that we're correcting for the environment, which might be contributing rather than the air that we pull through it. Okay, so next we want to get, now that we've determined the weights of the filter before and after, in the procedures, they'll tell you how many blanks you should be doing. For instance, I think in asbestos, you're supposed to do 2 blanks for every 10 samples. Okay, and depending, New York City DEP may have different requirements, may have more or less, but depending on the procedure you're relying on, it might vary a bit. But I think for the NIOSH procedure, it's at least 1 or 2 per 10. Okay, minimum 1. Pre-calibration. Okay, so remember we took our pumps. We calibrated our pumps either with the dry calibrator or with the burette. We calibrate them by taking 3 readings before we actually use them with a cassette in line. We took the average of those 3 readings and we recorded that as our starting volume. Okay, so well, first of all, I'm gonna go over here. I'm gonna put 10.500, and that's weight 1 is the weight before, I think. So I'm gonna put 000, and weight after I'm gonna put, just for my own purposes, 10.500. And the blank weight, I'm gonna say that didn't increase. Very frequently, it won't increase in weight at all. Sometimes it'll go down, which makes no sense at all. So you just kind of shake your head, but that's part of doing this work. So pre-calibration, let's say that before you calibrated, it was 1.8 liters per minute, right? Which is the average that you got before you started taking the sample. Okay, so after you're done, after you're done sampling, take the cassette off, you recalibrate that pump with another cassette, right? And let's say when you recalibrate it, it's 1.6 liters per minute. Now, these pumps, the more sophisticated they are, the better they are at avoiding differences in the before and after flow rate. They self-regulate to some degree. Not completely, though. What's a couple of things that might make the flow rate lower afterwards than before? The battery operated, right? Battery, you could be losing power on the battery, slows the motor down a little bit. What else? What's happening to that filter? Filter's getting clogged with dust, right? So it's resisting flow. Just the accumulation of dust on that filter might slow the pump down. So before it averaged 1.8. Afterwards, you took 3 readings, averaged them, and it turned out to be 1.7. So you don't know what it was at any given point in that, say, 2 hours that you were sampling. You don't know for sure what it was, but you can say, I'm going to average those 2 values and assume, even though it started at 1.8 and ended at 1.6, over that period of time, it averaged 1.7 liters. So you're going to use that average rate rather than these 2 rates. So let's say the pump start time is noon and the end time is 4 p.m., right? So how long did we sample? 4 times 60 minutes, 240 minutes. And the total volume sampled is going to be 1.7 liters per minute times 240 minutes, right? Minutes going to cancel out. It's going to be equal to, I can't do that in my head. I might have been able to at one time, but 7 times 240 is equal to 408 liters of air that we sampled, right? Remember that now we know that's how many liters of air we sampled. Liters of air, right? So now we can attempt to figure out what was the concentration in air. So the difference, W1 minus W2 minus W1 is 0.5 milligrams. And we're not subtracting anything for the blank because it was the same before and after. So it's 0.5 milligrams, right? Divided by, that's over a 240 liters, within 240 liters of air. But now I have to convert that into into cubic meters or 1,000 liters, right? So we can set up our formula with X is equal to 1,000, cross multiplying, and so on and so forth. Technically, it winds up just being multiplied by 1,000. And when you multiply by 1,000, right, it winds up being 500 over 240. It's going to wind up 2 milligrams per cubic meter. But you can take a look at now you can take this information then and go to the other document, which is basically a kind of an exercise or a report, and it discusses all of the details on how you actually took the sample and so on and so forth. On this first assignment, I did it for you, right? Illustrated the equipment and so on and so forth. Okay, and then at the end, I left you areas where you can take the information from your data sheet, fill it in here, and use the formula. Weight 1 minus weight 2 minus the blank 1 times blank 2 minus weight 1 over the air volume in liters that you actually sampled times 10 to the 3. That's liters per meter cubed. Liters canceled out, so it winds up milligrams per cubic meter, right? So, and then answer some questions. What's the total airborne particulates? What level? How does this level compare to the PEL? I know that it's not worker sampling, right? So, but just in general, a lot of times you'll do area monitoring because you want to have an idea of whether you really need to do individual worker sampling. If the levels are so low, even in the worst case that you're not anywhere near the PEL, you might not bother to do worker samplings to prove that to demonstrate the worker is not exposed over the PEL. What's potential source of errors? You can think about that. Maybe the scale is potential source of error. How about humidity, right? Moisture pickup and so on. It could be a number of reasons. So you can use your imagination, feed me back what you think might be some sources of error. What is the NIOSH procedure for total nuisance dust? In other words, how, and then a couple of questions here. How does the PEL, how does the NIOSH 500 procedure differ from what we did? In other words, what you would have been doing for an actual worker. How would the procedure differ if we were doing this for respirable dust instead of just total dust? Anybody know what the NIOSH procedure is for total dust? This was 0500. Bingo, there you go. So you can look up 0600 and you can look at the differences in the procedure and maybe feed them back a little bit. And like I said, I started to grade about a quarter. I got you about a quarter of it, stuff like that. I know some people had some issues, not so much with the weights, but with the volumes, and it's a little bit tricky with the volumes. So I'm going to stop there. I'm going to actually, I'll keep recording, and maybe some of what we do tonight will also be part of this as well.
So you get a chance to resubmit
this? Yes, you can. Yep. I opened it up again. I made the due date 10/14, which is, I think, a Wednesday night, right? Wednesday before a class. I made the due date for both the asbestos and the airborne particulates the same, which is like, I think 2 weeks from yesterday. The asbestos, I think only one person submitted that so far. Give it a try. I gave you a description of what I'm asking for, but more of a lab kind of format, kind of like asking you to kind of do what I've done there with a little bit more detail. Something 5 to 10 pages long, not enormous, not crazy, but maybe a couple of references here and there that you've looked up, information is about asbestos and so on. Give me some feedback, tell that on the types of asbestos, what asbestos is used for, where you're likely to find it these days, and so on. I gave you kind of a rubric, kind of a set of places, a set of topics to cover in the lab report. Okay, and you'll be able to, if you submit it by next week, I will have time to grade it and maybe give you some feedback, and then you can do it again before the end date. Okay, if you want to wait till the end date and you don't want to do it once, you can do that also. But I set it up so you can do more than one submission. Don't do 11 submissions because I have a life. I can't read all. No, seriously, you laugh, but you think that doesn't happen. So at any rate, let's move on to what we're doing tonight. Just getting over a cough, so I'm kind of a little raspy. Okay, let's move on from this. Any questions before I do that? Yes. Yes. Oh, there's like five. There's actually like four or five. Yeah, it's at the very end. It's on the on the Word document. Which document was that? Should I open it again? Are we talking the particulate? The asbestos? Oh, okay, let me take a look. Formal lab reports. Yeah, let me get to it. It's a little slow loading. Document 2. Okay, let's take a look at it. Simulated lab procedure. Oh yeah, I want you to figure them out. Yes. Yes. Yeah, yeah, you can submit it as two separate documents if you want to. But yeah, that basically that's simple. I mean that once you learn to count, you know what I'm going to do? What I'm going to do? Give it a shot yourself. Over this week, give it a shot yourself. Next week I'll start the class the same way. I'll review the calculations there. I'll use different numbers. I won't use those numbers, give those answers away, but I'll do exactly those kind of problems here. So you get a chance to do it on your own, submit it, see if you get it right, and then I'll give you kind of a review on and a hint on how to do it in case you need it during that session and record it, and then you'll have that whole week to resubmit it if you want to. Okay, yeah, I want you to answer those also. Yep. 5, 6, and 7. 1, report the average submit. Oh, you want to know something? The way that this lab worked was that it was an exercise in also using the microscope, right? Or how to use the microscope. So the idea there is that we wanted you to get an idea of the dimensions you were dealing with there, right? Under the same power as you were looking at and using the reticule to size things, right? If it's 100 microns wide and it's a crosshair and there's 20 lines there, each of those gaps is 5 microns. So I'll give you an example. The red blood cells we have, if we had, I would have loved to have stuck all you people with pins in order to get samples, but you'd smear some blood on a slide and you can actually separate out the red blood cells. And you'll see that it'll take up like a little bit more than one of those gaps. Red blood cells were typically around 6, 7 microns wide, millionths of a meter wide. Human hair might be 30 or 40 microns, right? Much wider. Fiberglass is looks like a log under there. They're really big. That puts into perspective how thin, sharp, and nasty these asbestos fibers are. They look almost dimensionless. They look almost just like fine lines compared to the size of a red blood cell, for instance. So once they get into your lungs, they pierce cells. They're very difficult to eliminate and so on. So you can, if you want, you can complete that. But I'll only look at the. I would love for you to just fill that in and just consider this. And you want to know something? Yeah, you should do it. You should do these. This one's simple enough. I gave you most of the answers right now. This one, report the fiber counts at the time. Make sure to identify. You can skip that because you didn't actually do the count. You'll be doing that in the report, simulating that. I gave you some parameters for that separately, right? And on this one, complete the following table. What's the area of a 25 millimeter diameter filter? What's the area that thing is, right? Well, you're going to come up with so many square millimeters, right? Pi r squared, 12.5 times 3.14, 12.5 squared times 3.14. What's the area of 20 millimeter filter? Why do I ask you that? Because the outside edge of that is covered up. You can't count it as part of the area that's been exposed. So the real area you're interested in is not the 25 millimeter, but the 22 millimeter area, right? So what's the area of that? So it's going to be 11 squared times pi, right? And that's going to be the area of the exposed part of the filter. Okay, what's the area of a 100 micron diameter field? Well, 100 micron is 100th of a meter, which is, 100 times 1 millionth of a meter. So 1,000th of a millimeter is 1,000th of a meter, right? So a millimeter is 1,000th of a meter, right? So there's 1,000 microns in a millimeter, right? So 100 microns is 1/10 of a millimeter, right? So if you figure out what's the area in 1/10 of a millimeter circle, right? It's 0.05 millimeters squared times pi. You can figure out what the area of each one of those little circles is, right? And then you can figure out how many of those little circles are in that 25 millimeter circle. And that's going to tell you how many fields that you have. In other words, what you got to multiply your average fiber count for in each field, what you're going to have to multiply it by the number of fields that are on that entire filter. I'm going to leave it at that. Next week, I'll give it a try from what I've just told you. Next week, I'll actually work that out so we can actually see it. And I'll go through some examples like this where I won't actually solve it with these specific numbers, but I'll take 4.5 fibers per field and I'll work through the same and different volumes. I'll work through the same kind of problem. So you can go back and see how to do this one if you need that kind of assistance. Actually, I like this last one the best, right? I like this last one the best because it twists it around a little bit. It tells you what the concentration is, and it asks you what must the average count have been if you had done the actual count. So actually what I'm going to do is maybe I'll make that extra credit because that one's a little bit more challenging. Okay, so yeah, give it a try at least. Now let's try it this week, especially because then you'll be able to, know if you've tried it, you'll know what you don't know. So it'll be a little bit easier if you figure out what's going on with it. Let's get to this other stuff. Okay, let's see. Okay. Now, I don't have a lot of working equipment, and Brian's not here, so anything that is his personal equipment is not available to me tonight, unfortunately. So I'm going to do my best to give you an overview of organic vapor sampling. We've up to this point, and the reason why I want to get this out of the way tonight is because I want to move on. Now that we understand there's a lot of different kinds of things that could be in the air that are potentially hazardous for workers or for the public, for instance. It could be particulates, it could be fibrous, it could be silica, which has a special crystalline material, has a special kind of hazard. It could also be organic in nature. Could be vapors, right? In other words, a lot of things are particulates. Pollens are particulate, mold spores are particulate, and so on. But then there's other things in the air which are vapors. They're gases. They're not actually particles. Things like fumes from or evaporated material from furnishings, formaldehyde, for instance, from solvents that you might be working with in a nail salon, acetone getting into the air. If you're welding or if you're soldering, for instance, the fluxes are organic compounds. They are liquids often or creams often, but when you heat them up, they vaporize. They actually turn into gases and they get into the air. So that's a whole different class of material. Since it's a gas in the air, it's going to pass through those filters. It's not going to be captured in a particle filter. We need another way of measuring and finding these particulates in the air, these vapors or these gases in the air. Okay, so this sampling of these organic vapors is going to be very important to us. A lot of really hazardous materials are present as vapors. You guys work in healthcare, right? So you work around disinfectants. Chlorine, for instance, is a gas. It gets into the air, it's hazardous. Formaldehyde, right? You work around glutaraldehyde, which is it's a suspected carcinogen, I believe, glutaraldehyde. I'm not positive. Formaldehyde, yes, for sure. But I think glutaraldehyde also, but glutaraldehyde has all sorts of other neurological effects and so on and so forth. And it's widely used in healthcare. It's used to disinfect dialysis equipment, to all sorts of other equipment and so on and so forth. And you deal with a million other solvents that evaporate into the air. You walk in somewhere, you smell an odor, that's typically a gas that's present in the air if you're sensing it as an odor. Even mold releases or gases into the air. They're called MVOCs, microbial volatile organic compounds. Even they release these materials into the air. And a lot of people are sensitive to these materials. There's a lot of concern that these could have their own toxic effects. If you are a painter, painters use all sorts of solvents. One of them is MEK, methyl ethyl ketone, which is a neurotoxin. So there's a lot of those kinds of materials that workers are exposed to. But since they're gases, the exposure is respiratory and they're gases in the air, we're not going to be able to sample them with a conventional filter. We're going to have to find some other way to sample them. Okay. So we're going to use the low flow pump as always, typically. One of the things about this, or any other kind of worker exposure, just to reiterate, the dose is not just the amount that's in the air. It's also how long you're breathing the air, how active you are in that environment as well. It's concentration in the air, but it's also got to do with the duration exposure and the amount of material that you're inhaling. In the lab that we normally used to do with this, we typically use toluene. Toluene is basically in everything. It's in furnishings, it's in carpeting, it's in all sorts of manufacturing. And somebody that used to run a GC lab used to tell me that if they got a sample of indoor air and they didn't have any toluene in it, they knew there was something wrong with the sample. Right? So there's little trace amounts of this stuff just about in almost any built environment. So that we used to use that because it was convenient and nobody would die immediately from it. So, or get really sick from it at the levels that we were dealing with. But it smelled like a chemical. So we were dealing with something that really is kind of a realistic thing you might want to be concerned about. Okay, it smells it's paint thinner. Liver toxin, kidney, blood system, central nervous system particularly, and so on and so forth. And some people find it pretty irritating. You can inhale it and you can absorb it through your skin as well. We're going to be mostly concerned right now with inhalation. Average worker, 10 cubic meters during a typical work day. Average person breathes about 20 cubic meters during a 24-hour day. The OSHA PEL at the time we put this slide together was 220 parts per million. Wait a second. Up until now, what were we measuring? Fibers per cubic meter. We measured milligrams per cubic meter. Now, all of a sudden, I came up with this new term called parts per million. Well, what the hell does that mean? We're going to have to examine that. 200 parts per million, as it happens, is equal to 754 milligrams per cubic meter. That's the weight of that gas in a cubic meter of air. I don't know off the top of my head, but at room temperature, standard temperature, and pressure, air has a weight, has a density and a weight. I don't remember off the top of my head what the weight of air is at standard temperature and pressure for 1 cubic meter of air, right? But the amount of, if that air has 754 milligrams of toluene in it, that has 200 parts per million of toluene in air. The ratio of toluene to air is 200 to a million. In other words, 200 molecules of toluene to a million molecules of air. We're going to talk about that in a second. I'm going to do some quick calculations. At the PEL, a worker would actually inhale approximately 7.54 grams of toluene. Why are they saying that? Because we just said a typical worker breathes in 10 cubic meters of air. Since there's 754 milligrams in a cubic meter at the permissible exposure limit, in other words, 0.754 grams, then if you multiply by 10, you get the amount of the actual dose, the amount that he would actually be breathing in during an 8-hour exposure. Look at the dimensions: 754 grams per 0.754 grams per meter cubed. times 10 meter cubes. Meter cubes drops out, and you get the actual exposure of 7.54 grams. These are the OSHA exposure limits. They may not be current. 200, there's a 15-minute ceiling level and a peak level, the most you can be exposed to ever. Okay, ACGIH, which is a little bit more in line with where it might cause health effects, is a lot lower than the OSHA limit. That's why I'm questioning the OSHA limit. I'm not sure if they've reduced it since we made this slide up. Okay, and the NIOSH recommended exposure limit is also lower than the permissible exposure limit. Okay, so let's think about this idea of parts per million. Let me escape this for a second and get up a piece of paper like this. I'm gonna do this. It's gonna take me a few minutes to do this, and then maybe we'll take a short break. Okay. Okay. So I'm gonna take something a little simpler. I'm gonna take ethyl alcohol, ethanol. Right? What's the formula for ethanol? It's 2 carbons, right? And OH, and a hydrogen, 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 right? It's 1 OH. A lot of times they'll show it at the end rather than there. Doesn't matter where, OH. It doesn't matter where you put it, right? There's 1 OH. That's ethanol, right? So let's say that, let's calculate the molecular weight of ethanol. Molecular weight of ethanol is equal to 2 carbons. What's carbon? 12, right? Okay, 2 times 12 is 24. Plus, how many hydrogens do we have? 1, 2, 3, 4, 5, 6, right? They're each 1 plus 6. Plus oxygen. What's 6? What's oxygen? There you go. So what's the molecular weight of ethanol? It's 24 and 6 is 30, is 46. Okay. What's the molecular weight of air? Anybody remember? Approximate molecular weight of air. What is air mostly? Nitrogen, right? What's the molecular weight of nitrogen? 17. I won't press you on that, but there's 2 of them, right? So it's 34. If you release ethanol into the air, is it going to rise or is it going to sink? It's denser than air is. It's going to tend to stay lower. It's really going to mix pretty well, but you know, it's close enough that it's not going to be really dramatic, but it's heavier than air is. Its molecular weight's heavy. It's a bigger molecule than the average air molecule is. The average molecular weight of, I think I got this wrong. I think it might be 14. I might be wrong. I think the average molecular weight of air is 29. I think it's 14. I think nitrogen might be 14. Nobody's helping me, but that's okay. It doesn't matter. It doesn't matter. It's not 20, and that's high. Okay, so why did I bring up this idea of molecular weight? Well, you guys may remember that there's a specific relationship between the molecular weight. What do we call 1 molecular weight represented in grams? Called a mole, right? There's a specific relationship between this idea of a mole, in other words, 46 grams of ethanol, right? What do we know about 46 grams of ethanol? How many molecules of ethanol is in that? Bingo, exactly. You remember what that is? 6. 10 to the 23rd, right? That's how many molecules there are in there. There's another thing that's important to note about what a mole is. And a mole at standard temperature and pressure occupies 22.4 liters of air, space, right? So if I have a cubic meter of air, how many liters of air? How many liters of air is a cubic meter again? It's 1,000 liters, right? Okay. So if I have 1 mole, 46 grams of ethanol, and I evaporate it into a cubic meter of air, right? That means that I have 22.4, that 46 grams means I have 22.4 liters of ethanol in 1,000 liters of air, right? This crosses out. This is unitless. Now this is parts per million. This is how much ethanol we have, at what volume of ethanol we have to 1,000 liters of air. Okay, so this ratio, 22.4 over 1,000, well, what does that turn? 22.4 over 1,000 means I move this over 1, 2, 3. It's 0.0224. Okay, so how many ppm does that represent? That, well, let's see. That's that 0. It's 22,400 parts per million. Yes. Well, yeah, we use the term parts per million. In other words, parts of air, parts of ethanol to parts of air. So yeah, it's a ratio. It doesn't have any specific units. It's just a ratio of how much air there is to how much ethanol to how much air. So parts per million, gee, has no units. But what is it? It's liters of ethanol to liters of air. It's a volume to volume ratio, right? So if I say we have, let me see what I had, what did we say was the permissible exposure limit for toluene, right? It was 200, was it 200 parts per million? So when I say 200 parts per million of toluene is the permissible exposure limit, what I'm saying is you can have 200 parts of toluene to 1 million parts of air, right? So if you wanted to figure out how many milligrams per cubic meter that represented, right? You would have to convert that. You'd have to figure out, well, let's see, if this was cc's, right? This would be 200 cc's of toluene, right? So this is a million cc's of air is equivalent to a cubic meter. So this would be 200 cc's of toluene. It's volume to volume. So how many milligrams is in 200 cc's of toluene? Well, we know that 22.4 liters, or in other words, 22,400 cc's of toluene contains what was the molecular weight again? 46 grams of this material, right? So how much is 200 cc's? Did I get that right? Right. Yep. That's for. I'm sorry. I kind of forgot. I don't know molecular weight. I think it's 100. I think molecular weight of toluene is 100. That's one of the reasons why we use it. 100 grams of toluene in that volume, 22.4 liters, in that volume of air represents 200 parts per million. Excuse me. 200. This volume in a cubic meter represents 200 ppm. Okay, so 20. I went away from this. 200 ppm of toluene, million parts of air. That's cubic meter. 200 cc's of toluene. So in 2200 400 cc's, there is 100 grams of toluene. So now I have to figure out how many grams there is in 200 cc's. So X over 200 is equal to 100 over 22,400. In other words, this represents that ratio that we're interested in. That this represents the ratio that we want to duplicate with 200 cc's. So it's going to be 100x is equal to 200 times 22,400. Did I do this right? Oh, I'm sorry. It's 22,400. X is equal to 20,000. Got that right? So 20 divide by 22,400, divide that, X is equal to, it's approximately 1 gram. So 200 parts per million of toluene is roughly equivalent to 1 gram per meter cubed, I think. And that's what it was, right? Wasn't it 0.745? Right? I might have gotten the molecular weight a little bit wrong, but that's roughly what the equivalent was when we just looked at that slide. It was roughly 3/4 of a gram. Okay? I got one because maybe toluene is not exactly 92. Yeah, so there you go. Okay, so like I said, we'll go over this again a couple of times. But let's take this as a first shot. It's 7 o'clock. Let's take a break. Okay.
Nitrogen is 14.
Yeah. So there you go. Yep. 28. So roughly 29 average for air. So yeah. So you can figure this out. So if you have natural gas is methane, right? Principally, carbon is 12, and four is 16. So if you get a natural gas leak, is it going to hang around the floor? No, it's going to tend to rise, go up. Yes. Yes. Okay. Let's see. CS. Trying to remember what the. Yeah, let me take a look over it. Looking at here. 2.3 average count minus the blank. Right, is that what the blank was? Average blank, yeah, that's a blank. You subtracted the average count, subtracted the blank from the average count. So that gave you the actual number of fibers that were picked up, right? And then on the bottom, we have the area of that's the area, the field area, right? Times the sample time, times the flow rate, times 1,000. And at the top, we got 385, which I think was a constant to make up for the.
385, I believe, is the filter area.
Oh, the 385. No, the field area is. Oh, the filter area.
Field area.
Gotcha. Okay, so this over this winds up being the number of fields. So you're taking the average times the number of fields, right? It's what that works out to be, and then dividing by the number of cc's down here. This is right. That should work out. The way you got it set up is right, so that should work out correctly. Yeah, I like looking at it this way. This is the average fibers you have per field. The 385 is the area of the filter, the portion of the filter that we could capture stuff on, divided by the size of that circle. So taking this and dividing it by the size of that circle gives you the number of fields. So if you have 2 fibers per field and there's 5,000 fields, you got 10,000 fibers. So that's what you're doing there. And then on the bottom, you're dividing it by the number of cc's, number of cubic centimeters or milliliters of air that you pulled. Hang on just 1 second. So that's going to be the flow rate. What is that? 312 is the time times the flow rate times 1,000 to turn it into cc's instead of liters.
Okay.
Perfect. Yes.
Sorry, quick question. These slides, I went to go print them out. They're not, I don't know if you enabled them or not. I can't, I always print
I have a PDF version of it on there.
It's not there. I just checked that for it.
Oh, yeah?
Yeah, because I've been trying since this morning.
Hang on. I changed it a few times. You mean the asbestos one? No, you mean this
All of
tonight.
these are up, but because I like to follow you while I'm.
Oh, you mean the VOCs?
Mhm.
Oh, yeah, look, they're not there.
Yeah,
How did that happen?
I don't know.
I put them there. Okay, I got them. I'll put them there right now.
Okay, I just want to print them out before you start.
Okay, hang on a second.
Okay.
Let me browse my computer. I can't understand. I know I put them there.
It just disappeared.
I got no idea why that would happen. hang on a second, that's the PowerPoint.
Yeah.
This is where is it? That's the PowerPoint. This is the PDF of the PowerPoint. This is the Word document. And this is the PDF of the Word document. So all four of them should show up.
And I think a few people requested on the discussion board if you were going to upload the videos. I think I emailed it to you too, but I know you're super busy.
Oh, you know, I'm going to go back and see how many of them I can recover.
Okay, yeah, if possible. It's just it's nice to look at, especially when we're doing like conversions, like for
Yeah,
today's type
I
of.
understand. Yeah, I'm hoping actually next week. Next week I'll actually do it a little bit more smoothly. I'll have it set up.
Okay.
You know, especially if you get a chance to actually do the lab.
Yeah, exactly. All right, it looks like it's all there. Right?
Yep,
All right, I'm gonna go
that
print
should
it
be
out.
accessible.
Perfect. Thank you so much.
Yes,
I know that's on the syllabus that we have an exam coming up.
I'm going to change the date of it.
Oh,
Okay, but just so you know, I think it's going to be the 24th. Hang on a second.
is it gonna, are we gonna have a review or?
We're going to have, definitely we'll do some sort of online review or something like that before it.
Mhm.
And my plan is for exam one to make it online.
Online?
Okay, open, it's going to be open book and online. There's a reason for that. I have to be out of town that night. Okay, that's why I'm changing the night and doing the exam when I have to be out of town.
All right.
But there'll be a final also. But the idea of these labs is I want to get these labs to a point and the exercises, so you get like a good grade on them. In other words, resubmit them so you get a good grade on them, and then like you have like a good grade on the exams and the labs. I mean the labs and the exercises. It'll diminish like a bad night on the exam or something like that.
That's a good question. But the
Holding
lab
it,
report, the specimens, right? So the lab report was saying like the instruments will be performed in class. Where we're gonna talk about like the little instruments that we took outside and we're gonna like.
Oh no, that's a separate lab. That's particulate. That was particulates using a direct reading instrument. The asbestos was the week before.
PCM.
Yeah, it was PCM, right?
Right. But it's asking the lab report what instruments we use, what did you perform in class. I'm like, do we need to
Look up the NIOSH procedure.
Okay.
Right.
Yeah, because I followed it. So I'm not sure if you took me the same.
Yeah, if you look up the NIOSH procedure, it'll tell you the equipment that you should be use that. Yeah, use
Like
what
the
they.
measurements.
Yeah,
like
what kind of
counting
microscope? It says what kind of microscope, what kind of scale you should use
Oh,
to measure the way. The NIOSH procedure outlines exactly what you got to have.
okay, because I wasn't sure if I had it.
Right. Yeah, if you don't have a manufacturer's name, don't worry about that.
Okay, yeah. that's
But
what
it'll
my
give you the.
answer.
In fact, I think it gives you in the NIOSH procedure. It even gives you some recommended manufacturers
Yeah.
that are acceptable, like such and such, or equal, or
Yeah.
something like that.
And
Yeah.
this, sorry, one last question. For this calculations for
Yes.
5, 6, 7, I use it based on this chart.
Yeah. Use the 22 millimeter.
Right, I
Right.
use the field, exactly.
Right.
Yeah.
Exactly. Use that, and it turns out that area is 385 millimeter
Mhm.
squared. Right. So and then the field is 100 microns, which is if you figure it out.
Yeah,
If you
I did
do
a
it, it's
calculation.
0.003.
Yeah.
Whatever it comes out to.
Yeah, okay. Wanted to know.
Yep.
Thank you.
Yes.
This looks like so this number 8. I have like set it look like this.
Ah, good. Okay. So you're doing it the other way around. Let's see.
It starts on the other page.
Oh, I think.
Starts
Yeah.
on this page.
Yeah, let's think about this for a second. Oh yeah, okay. So the concentration is equal to CS stands for
Average count.
average count. Okay. Okay, so the average count minus 0. Okay, good. Times so yes, you should be able to solve for that.
That costs multiple.
Yeah, you work that out. That's going to be equal to 385 times the average count.
I switched it around because I put CS on this side.
Oh, I see. Okay. Yeah, no, I'm not that smart. I have to go through it. 385 times CS over all of this. You could actually calculate that right off the bat. Okay. Actually, you brought it up there. Okay.
I got
CS
calculated.
CS times 385 is equal to CS times 1. CS times 385. So 385 goes on the bottom. Yeah, it looks right to me. Because here, what's going to happen here is put this over 1, right? So this is going to be CS times 385, right? Is equal to this.
Times all that.
Okay. that times this,
Mhm.
and then you're going to divide by 385. So all this is going to be on the top, and then 385 is going to be on the bottom, which is what you did.
Mhm.
Good. Yeah. No, you went. That's right. That looks right to me, actually.
Alright.
Yeah. Good work. It helps to know a little. It helps to know a little bit of math in this world. Okay. So. Okay. So. Okay, guys, I'm going to get started again. So, okay, just in time, just about to get started again. Okay, so now that we've discussed what this idea of parts per million or concentrations, which we can express either as a unitless measurement called parts per million, how much of a gas per million parts of, how many parts of the gas per million parts of air, which is unitless, basically, it's liters per liter, per liters, that we call parts per million. We can express it that way, or we can express it as a weight of the gas in air, milligrams of a gas in air. A little counterintuitive to think about a gas having weight. So, and it's really odd because it's weight of a gas over the volume of another gas, right? So it's not kind of a mix of two different kinds of measurements, but you can use either one. The PELs are often as parts per million, but they also are easily converted into millibarons per cubic meter. Now, I struggled a little bit with the conversion because I had to remember what the molecular weight was, and then I got the formula over here, and so on and so forth. You can go online and find calculators where you can put in one measurement, the milligrams of a material that per cubic meter that you have, and the molecular weight of the material, and it'll calculate how many parts per million you have. So you don't actually have to do this yourself in your head. You can actually download an app that'll do the conversion for you as well. What do you need to know? You need to know the concentration in the air in parts per million and the molecular weight in order to find the how many parts per million it is. And if you know how many parts per million it is, you need to know the molecular weight in order to convert that into milligrams per cubic meter. So the molecular weight allows you to go back and forth on those conversions. Again, if you don't want to do the math, you can always go to an app that'll do it for you. Or I'll give you some sort of kind of guideline to calculate. In other words, plug it into this formula to go this direction, or this formula to go that direction. Not to mention the fact there's plenty of places where you'll find that as well. Okay, you can still see that stuff, right? Here we go. Okay, so how are we going to measure these vapors in the air? Well, we already took a look at one way that we were going to do that. Carbon dioxide, they are gases in air. Carbon dioxide occurs naturally, and it also occurs because we're breathing into the air or because in combustion, and the combustion product is carbon dioxide, so it builds up in the air. Carbon monoxide, a more dangerous combustion product, winds up in there as well. And we know that we took these Draeger tubes, right? We were talking about using these Draeger tubes. I have a couple of different versions of it here, right? This type here. Here's another version of this. This particular one takes a cassette where it can measure several gases at the same time. The cassette has multiple tubes in it. You shove it in here. You can actually set this up to time the amount of time and slowly draw air through those tubes so you can use it to measure over a time-weighted average over an extended period of time, or you can use it to take short-term readings as well. But that cassette that you would put in here could hold up to, I think, 5 or 6 tubes, and you can measure multiple different gases in the air at the same time. Same thing as these pumps, except this automates the process. Okay, you can see several different kinds of these pumps for different gases that you might measure. There's another company, accuracy is not great, but they're used kind of like as a rough measure of what the levels of presence of these materials might be in the air, but they have tubes for hundreds, possibly 1,000 different gases. The next option that we have is direct reading instruments. Remember, we had that particulate monitor that optically measured the amount of particulate in the air. Well, we also have devices that will detect and measure the concentration of gases in the air. We talked about one type of several types of these kind of devices when we spoke about direct reading instruments last week. One of the main ones that you'll use in practice as an industrial hygienist, there is a person that tests indoor air quality, for instance, or goes in and investigates hazardous waste sites, is a photoionization detector. Okay, and we have one here. This one is called a mini ray or a PPB ray. PPB because it'll measure VOCs down to a part per billion concentration. Okay, and this has a little pump in it. This one doesn't unfortunately work, but it has a little pump in it. I'm going to show a video of how this actually operates. It has a little pump in it, draws air into this device. It's portable, and it's pretty sensitive to many different gases, literally down to part per billion levels. Okay, now the thing is that this photoionization detector uses a high intensity ultraviolet light to ionize the organic vapors as they're being drawn through here. So that high intensity light only works for certain class of compounds that can be ionized within the energy range of that lamp. This one has a 10.6 electron volt lamp, I think similar to the one that you see there. Might even be the same instrument. Okay. I think last week we actually showed that which gases it might not be able to ionize and which ones it could ionize. Now, this thing needs to be calibrated just like anything else. It doesn't distinguish between gases. It detects organic vapors that have been ionized, but it doesn't know what that vapor is. You have to tell it, you have to determine for yourself what that vapor is, and it might not be as useful to you if you have a mixture of organic vapors in the air. Well, a lot of times that's not the case. You might be interested in measuring the level of methyl ethyl ketone in an MEK in an area where in a paint spray booth, for instance, where there might be a worker exposure. If you know the material being used as methyl ethyl ketone, you can use this really effectively to detect it and to measure the concentration of it. Now, in order to use it properly, you have to calibrate it so it understands how much methyl ethyl ketone is present. In order to calibrate it, you need something that has an exact concentration of the gas that you want to measure. Well, you know, they don't really, it'd be pretty hard to find an MEK standard to calibrate this with. So what you do instead is you take another gas. Because typically they use a gas called isobutylene. Okay, and this is this particular gas. This cylinder has exactly 100 ppm by volume of isobutylene in pure air. Right, that's what we have here. So you use this device to calibrate this. You turn it on. Let me latch it. So there is This regulator says that there's 0.3 liters per minute of isobutylene, isobutylene at this level in air escaping here right now. So use a tube. You can calibrate this, connect it to this device, and you can use it, which is matching the pump flow rate of this, right? That's why it's this particular regulator. You can expose this device to that level and calibrate it to that level so it understands that this is what 100 ppm of isobutylene looks like. Well, that's nice. You only have one point that you calibrate it to, but it's nice to have more than one point to calibrate to. And what you can do then is that you can take, I have some of them here, I think. You can take a tube with activated charcoal, which would eliminate isobutylene if it were present in the air. There's little ones here somewhere. I'm going to take this big one for the time being. And you can connect it to this activated charcoal tube. And this instrument, and then you can train this instrument then to recognize 0 ppm isobutylene. So you have 2 points. You have 0 and 100 ppm. And it can assume that the concentrations are linear in terms of how much it ionizes. And now you can measure any concentration of isobutylene between 0 and 100 and be pretty reliable. Well, the problem is you're not interested in isobutylene. You're interested in methyl ethyl ketone, MEK, right? And you don't have a standard for that. So the manufacturer for this instrument has determined that if you have a certain reading based on the way this instrument with this bulb will ionize organic vapors, that if you substitute methyl ethyl ketone for the isobutylene, then this instrument might only read half the correct level of MEK. So they used to give you a table, a book with a table in it, and says, well, if you calibrate to 100 ppm isobutylene, then, and you use it in an environment where you're measuring MEK, then you multiply by, say, 0.6 to get the correct reading for MEK. So that's how you use this for multiple gases. In fact, this one, because it's got a little computer in it, this one actually has a table of 100 commonly used industrial solvents that you can just calibrate to the isobutylene and then tell it to measure for ethanol, for toluene, for whatever gas is in the environment that you want to look for, and actually use it to measure that reliably. Okay, and use the calibration, this technique to do a measurement for other gases as well. So I'm going to pass this around just so you can get a handle on it. I'm going to play a video that shows you how to use it calibrated a bit. And we have some other side kind of devices with it. I'm sorry I don't have it that's actually working. And I think that next week if Brian's around, I might be able to dig one up. I think when I asked him about it, it was in the field, somebody was using it for that capstone or something like that. Okay, and we discussed how this works. Okay, the UV light provides the energy to ionize the organic molecules so that it becomes conductive, and that's how they actually measure the concentration of that gas. Well, it's nice from one perspective because it'll measure a specific gas out of a catalog of gases very accurately. But on the other hand, if it's a mixture of gases, it's a little bit less useful, because if you have MEK, but you're also using acetone and you're also using toluene in that environment, well, now you don't have a table for that, right? So it becomes a little less useful. You can use it to measure kind of intuitively total VOCs to see what the combined level might be. The other thing you can use it for, if you have an odor source that's hard to track down, you can actually kind of like skirt around and use this as a sniffer to determine where it's most concentrated and where it's least concentrated to help you find the source of that organic vapor. A lot of indoor air quality complaints come in that, gee, we have this odor, we don't know where it's coming from, what it is, and so on and so forth. You can use this sometimes usefully to like try and figure out where the concentrations are highest in a facility, and then try and deduce where they might be coming from in that case. I'm sorry. You know, that's a good question. I think, yeah, that's pretty strong odor, and I think there's enough VOCs coming off of them that you might be able to do that. Yeah, it's not the most reliable thing in the world. Sometimes they work pretty well. Sometimes don't. These kind of odors, those kind of indoor air quality odors, are sometimes the hardest thing in the world to track down. Yes, MVOCs. Yeah. The concentrations could be very low, so you might or you might not. So yeah, I think there's a possibility in an area where there's very little VOCs in the air that you might be able to detect a difference in the area where you're smelling that. But it can be pretty tricky. I mean, you've got mold behind the wall or the ceiling or something like that. Again, sometimes going to be very tough to find. Find an area where it's higher that where it's kind of escaping into the room or mixing into the room. Let's see if I can't get this to play.
The Mini Ray 2000 comes with an instruction manual, a calibration certificate, external charger, CD software, data transfer cable, zero filter, and technical note TN106. Unpack and confirm you received everything. Galson Laboratories will preset the unit to your custom settings or a standard setting of 1-minute data logging intervals calibrated against isobutylene.
You'll notice in the bottom of it,
EV
there are two ports. One of them is for a
push the
charger,
on button
and the other one is
allow
for
the
a
unit to go
connection
through
to a
minute of
computer.
Diagnostics checks. This will take approximately 2 minutes to complete. Once the unit has gone through the diagnostic phase, it will begin to take readings and data log results. Although Galson Laboratories zeroes the unit before it goes out, we recommend that you re-zero the unit before each day of use. If you have a known concentration span gas available, a bump test is also recommended. To re-zero the instrument, press the mode button and the N button at the same time and hold until data log paused appears on the screen. This will stop the unit from data logging, and the unit will ask you if you want to calibrate. Push the Y button. The unit will ask you if you want zero air calibration. Push the Y button again. The unit will begin zero air calibration while you install the zero carbon filter. Attach the zero carbon filter with the arrow pointing towards the unit and press Y. The unit is now re-zeroing.
A lot of times
When
you just use an
re-zeroing is
activated charcoal
complete,
tube as
the
well.
screen will display reading 0.0. Push the mode button until the unit shows the flashing L, indicating the unit is collecting data and data logging the results. Remove the zero carbon filter and install the water trap filter. You can now move from sampling point to collect your data. The rechargeable batteries will last approximately 8 hours before recharging.
It's a particulate filter just to protect the
When your
probe
sampling
on the
event is
inside.
complete, you will need to download
The
the
sensor.
data to a PC to print out a report. Galson Laboratories will download and print out your report on request. To do this yourself, press the mode button several times until PCCOM ? Appears on the screen. Push Y and pause monitor ? will appear. Push Y again. Attach the data transfer cable to the bottom of the unit and to the COM port on the PC, with or without the USB converter cable. Load the software CD and follow the online instructions. Open the Communications tab under the toolbar, set up port, and select COM port. Press the RECD icon with an arrow pointing to the left under the Communication tab in the toolbar. Click OK and data will start to be downloaded. When data transfer is complete, the report will open up so you can save, print out a copy, or import to another document. When you have completed all report functions, disconnect the unit and shut down or remove the CD. Push the mode button once on the unit to go back to the survey mode. Hold mode button for 5 seconds until the unit turns off.
Okay, get it? There's two modes: data logging mode, and survey
Repack.
mode. Oops.
pilot lamp ionizes volatile organic compounds. The ionized gas then passes over a sensor which detects the charge and then converts that signal into a current. The current is then amplified and displayed on the unit as a reading in parts per million. The Miniray 2000 detects VOCs at a range of 0 to 10,000 parts per million. It features real-time readings and data logging capability. For calibration, we will need the following supplies: a canister of isobutylene at a concentration of 100 ppm, a regulator, and a Tedlar bag. Also, please remember to always use an external filter whenever using a PID. To begin,
The reason for the external filter, you get dust on the sensor on this thing. It's going to interfere with the reading, and if that happens, then you got to take a little bit of solvent. You got to put your gloves on. They give you little finger cuts to protect your fingers from the solvent. You got to get your Q-tips out. You got to clean the sensor off. It's a real hassle, right? So that's why you want to avoid getting that sensor dirty. So typically, when you use this, you would want to connect this simple filter to it. Oops. What happened?
the next menu item.
So they talked about a
Once
bump
the
test.
pressure calibration is complete, open the valve on your Tedlar bag and make a secure connection to the probe tip of the unit. The display will read span cal. Press the Y button to start the span calibration.
And it'll run 0. I'm not going to finish this because we
Main
just
display.
really saw this
You should notice
previously.
that
When they mention bump calibration, that's not really a calibration. What they're saying, for instance, is if in the field you don't want to bring the canister with you, you can fill this Tedlar bag with the isobutylene. You can use tubing and actually pump it up and fill it from the can. Reminds me. I want to make sure I'm not filling the room. I'm not wasting the calibration gas. I'm not worried about the isobutylene. I'm worried about wasting. I'm not worried about getting into the air. I'm worried about wasting it. So at any rate, you would fill this with the standard you want to use, and then you could connect this. It has a pump on it. It's going to suck out of it. You can connect this to the device, and you can just simply take it out into the field. And if you don't want to do a full calibration, you can just read what's in the bag. And if it's reading 100 for isobutylene, you say to yourself, it looks pretty good. I don't think I need to recalibrate it. So it's kind of a short, that idea of bump calibration, it's not a real calibration. It's kind of a shortcut. The other thing you can use these bags for is if you want to do VOC readings, you don't have a portable a device like the PID, and you don't have a portable gas chromatograph, you can actually use a pump to fill this with room air and then send this to a laboratory. They will suck the air out of here and condense any organics that might be in here and inject them into a GC or GC mass spec to take a reading, right? So you can actually fill these with room air. Instead of these, they have other devices, which I think that we're going to come up to in a few slides that'll help you take a grab sample or a continuous sample as well. Yes. Yeah. If, in other words, if you didn't have it with you, you could fill the bag and then take it back to your office or something like that and take a reading with that device. Yeah, absolutely. Okay, passive dosimeters. Many manufacturers manufacture these devices that work by diffusion. They have activated charcoal in them, or they have some other material, some sorbent material other than activated charcoal. And the idea is that these badges can be placed on a collar, can be hung from a vent or in a room or something like that. And they come in a canister. I'm going to show you a demonstration of it. They come in a canister that's sealed up and they have no VOC, they have no organic compounds absorbed onto them. Okay, and what happens is that you can put this on a worker's collar over the course of an 8-hour day. If he's exposed to glutaraldehyde, for instance, the amount that will be absorbed onto that sorbent badge is going to be proportional to his exposure. And they have, the manufacturer will have done experiments where they monitor in an environmental chamber, like what the level of glutaraldehyde is and what the amount that's absorbed under different conditions, temperature, and so on and so forth. They will ask you to take this device, send it back to them, give them the environmental conditions, how long you exposed what the person, how long you exposed it, what the temperature was, what the humidity was, and so on and so forth. And they'll report back to you and tell you that the average amount of the VOC that you're using this for is at most likely at this average concentration. So you don't need a pump, you don't need other devices. It's not as accurate as doing it with the PID and with other kinds of devices, but it's certainly a hell of a lot more convenient, and it's certainly a lot easier for the worker to deal with. So they have badges like this for glutaraldehyde, for formaldehyde. 3M makes a badge where they will do multiple analyses on a single badge for 3 to 5 different VOCs that you specify. Okay, those are called passive samplers. Hang on. Okay, and I'm hoping that this will come back here. There we go.
Before monitoring with the 3M 3500-3520 organic vapor monitor, record the following information in your data log: the monitor serial number, the ambient temperature and relative humidity.
That's important because it's going to affect the absorption of other compounds.
And the employee or area ID. Remove the diffusion monitor from the can. Record the date, employee or area ID, and sampling start time on the monitor label supplied, and the relevant information on the base of the OVM itself. Do not remove the white film and plastic ring. The white film is a dust cover to prevent dust buildup inside the monitor. It does not prevent the organic vapors from passing through to the charcoal absorbent pad beneath. The OVM can be used as an area or personal sampler. For personal sampling, attach the monitor near the employee breathing zone. When used as an area monitor, hang it somewhere away from walls, corners, tabletops, or other regions where the air movement in the room may be limited. Remember, a field blank should be collected for each sample set and should accompany the monitor during all periods except actual sampling. For more detailed information, watch the Golson Field Blanks instructional video. After the sampling period is ended, remove the outer plastic ring and white film from the monitor using a coin or other lever. Be sure to move to the next step immediately. When using the 3M Organic Vapor Monitor 3500, snap the elution cap with plugs onto the main monitor body. Be sure the 2 port plugs are pushed closed securely. Record the final sampling time on the back of the monitor. The OVM is now ready for shipment. When using the 3M Organic Vapor Monitor with backup section 3520, snap an elution cap with plugs onto the top of the primary body. Separate the primary or top body and secondary or bottom body sections by pulling or leveraging them apart. Snap the bottom cup.
Yep, losing the sound for some reason.
Snap clinical results will be compromised. Return the sealed monitor sections and the short plastic straw to the can and close it with a white plastic lid provided.
35, 3510, 3520 are used for different gases.
Complete the chain of custody form. It is important that you include all the information
we should spend like maybe
a
half hour on chain of custody at some point.
Remove the pink copy and keep this for your records. Send the white and yellow copies in with the samples to the lab in the large Ziploc bag. Questions? Secondary or bottom.
I just want to point out something.
3M Organic Vapor Monitor 3500.
Oh, it doesn't stop when I click it. Hang on a second. I just want to point something out on this video. You notice that there's 2 ports there? Okay, keep that in mind. We're going to talk about that in a second. There's 2 little openings. You pop them open and connect something to. That's going to come up in just a bit. Now, what's the classic NIOSH method, OSHA method, for sampling organic vapors in a worker's breathing zone? We need an 8-hour time-weighted exposure. We need a precise way of measuring the volume of air that we measure We need a precise way of measuring the amount of material that's in the air. So the NIOSH procedures for most VOCs are very similar to what we did with asbestos and what we did with particulates. We use a portable pump. We calibrate the pump. Instead of a filter, we use a tube which contains activated charcoal. Here we go. It's about this size. This tube contains activated charcoal in it. I'm going to pass this around with its ugly big brother over here. When you take a close look at this tube, take a really, really, really close look at this tube. And it's really hard to see on the small one. That's why I brought the big one. Okay, and what you're going to see is that this one's sharp, so be careful because somebody's broken it. What you're going to see here is that there's two sections to this activated charcoal. There's a little foam separator separating the two sections. Okay, and there's a little arrow which indicates the direction of airflow. You would connect this by tube to your pump in place of a PVC or a cellulose ester filter, right? Instead of the filter we would use for counting particulates, you would use this. And this can be mounted in a holder, which can hang from the worker's collar. So the holder is holding this thing, and it's going over to your pump. You've calibrated the flow rate on the pump. This is exposed for an 8-hour workplace exposure, so it's a relatively low flow rate typically, and air is pulled through here that's in the worker's breathing zone. If it's got VOCs in it, some of those VOCs will be absorbed by the activated charcoal, right? And it's going to get absorbed into this first section, the first part of the activated charcoal that it's exposed to, right? And then you got the little foam part, okay? So when you are done, right, you know how much volume of air you've pulled here. Now you got to know how many milligrams of VOCs that you've captured on the activated charcoal that were in the air. Also, maybe you need to know what kind of VOCs that you captured on here as well. So this you could use two ways. One way is to identify what's in the air, but also to measure how much is in the air. Let's just talk about, we know what it is, like acetone, and we want to make sure that the worker that works with acetone, say a nail salon worker, is not exceeding the OSHA permissible exposure limit in their breathing zone. So they wear this for 8 hours. We then take it, we cap it, we send it to the laboratory along with a chain of custody. The laboratory breaks this and separates these two sections of activated charcoal. The part that we're interested in is the first section, because that's where the stuff got captured. They take that, they mix it. There's two ways that they can take this and put it into a GC. One way is thermal desorption. They take the activated charcoal section, they put it into a little tiny chamber, and they heat it up. The heat drives the VOC off into the GC. The GC then works to have it go through the column and eventually come out and get it detected in the flame ionization detector at the very end. And you see a peak, and the area on the peak is the amount of the material that was in here. And they report to you how many milligrams of acetone were absorbed on this. You know how many milligrams, you know how many liters you collected. You can convert that into milligrams per cubic meter and into parts per million as well. Anybody know what the second section is for? Think about it. Why would you have a second section on here? If you got the right idea, but you're measuring all of it, all of the stuff gets captured on the front section, and then you got this second section. Let's say that the amount of VOC in the air is more concentrated than you expected, and it saturates the activated charcoal. Some of it's going to get into the second section. So they test the second section as well, just to make sure that you didn't miss any. That's considered what they call breakthrough. In other words, you have the concentration was too high, you sampled too much air, you pull the sample air thread through there too quickly because it takes a certain amount of time. In other words, you got to move slowly because you want the activated charcoal to absorb it completely. If any gets into that secondary part of this tube, chances are you're going to throw it away and start again, which is a problem because now you got to go back and do the sample again. Yes?
The temperature of the environment has something to do with
The absorption?
absorption.
Also, the humidity will also have something to do with absorption. Yeah, so there are issues. In fact, they're probably addressed in the NIOSH procedure. In other words, it's intended for a certain temperature range and humidity level and so on and so forth. So that can have an influence on that. And some of the techniques may ask you to also put a sorbent on here for moisture. In fact, some of these Draeger tubes that we have, you may have noticed that they're multi-section, and those first sections might be to take moisture out. It might also be take chemicals that might be in the air that are confounders that'll also change the color of the tube that are not the target gas, right? So sometimes you have to do something to protect it from that. So yeah, that's called breakthrough. Okay, so one way is to desorb this thermally. Another way is to take this activated charcoal, put it into a tiny beaker, let's say, and they add a liquid to it, a solvent, commonly carbon disulfide. Carbon disulfide has a real affinity is a really good thing to dissolve, a really good solvent for many organic compounds. The activated charcoal is desorbed by the carbon disulfide, and then they take that, they know they have exactly 1 cc of carbon disulfide, so they know that they've removed the material from the activated charcoal and it's in that 1 cc. So now they can take a micro cc or something like micro milliliter of that, a few micromilliliters of that material, inject it into the GC and see how much of that VOC is detected by the gas chromatograph. And then they can work their way back to, well, if this is how much we put into the GC, and this is how much must have been in that 1 cc, and this is how much was in the volume air they pulled, and so on and so forth. So there's a couple of ways they can get the material from here into the GC. I'm going to pass this around. Okay, there's many different kinds. Activated charcoal is not a good solvent, not a good absorbent for everything. Sometimes they use Tenax, which is a plastic-like material, and sometimes they use a silica gel or some other material. Silica gels are used very frequently for polar compounds, materials that have polarity on their molecule. Okay, so, okay, good. There's a picture of the front and back section. That's the mini tube. That's not the big tube. Okay, now, I mentioned to you that this idea that you might underestimate or overestimate the amount of, you might overestimate or underestimate the amount of VOC that's in the air, so that you have to go back and you get breakthrough or you don't get enough of the VOC, so you have to go back and resample again. Well, they have these devices that are holders for these tubes, right? This would hang from a worker's collar. And this device allows you to put 2 tubes on at the same time, and they have little screws where you can adjust the flow rate through them on the side here and on the side here. You can adjust the flow rate. So you can calibrate your pump so you're getting a half a liter per minute through one tube and a liter per minute through the other tube. So you have a wider range, less likely to undersample and less likely to get breakthrough as well. So if you get breakthrough on one tube, then hopefully the tube that you took at a lower rate will still be usable. So you don't have to go back and resample. Okay, and you have some of these, you have multiple tubes. Okay, you do the usual calibration. Same technique. Okay, so now what we would have done with a laboratory exercise is that we would have taken a sample. We used to have it like what we call an environmental chamber. It was a big plywood box, right? So we would set up pumps like we did with different particulate monitoring. We get the pumps running, calibrate, we get the pumps running, and we would put them inside this environmental chamber, and then we would splash some acetone or toluene into the environmental chamber and absorb this material onto these tubes. Unfortunately, even then, we didn't have a GC or a budget to send it out to a lab to analyze it. So we would have to go through the exercise. Here's an example of how a GC, we talked about briefly about how a GC actually works. And I think this will give you a little bit better picture of it.
Gas chromatography, GC.
We're almost done. I'll tell you what, let's just watch this video and we'll call it a night.
To mixtures of fairly volatile liquids.
Volatile liquid. I love that. I love the accent.
Chromatographic methods. There is a mobile phase.
Mobile.
A gas that carries the components of the mixture over a stationary phase. In this case, the stationary phase is a tube called a column, packed with solid or coated with a high boiling point liquid. The components of the mixture leave the column in order of volatility, the most volatile first. This is the complete instrument, with the computer control system on the right. The sample is injected here. From this injection port, the sample passes into the column, which is kept in a temperature-controlled oven. Columns are normally wound into a spiral to save space. This capillary column is 30 meters long.
Capillary. Great.
This is much shorter, about 1 meter.
How many of you guys know who Monty Python, what Monty Python is? A few, right? Some of the older guys? I just went to a reading of an interview with Eric Idle, who is one of the main writers and characters from Monty Python. He has a new book out.
And the less it interacts with the stationary phase, the faster it travels through the column. At the other end of the column is a detector that detects each component of the mixture as it comes out of the column and also measures its amount. This instrument has a flame ionization detector, which consists of a hydrogen flame burning in air. As a substance leaves the column, it burns in this flame, producing ions, which can be detected by measuring the electrical conductivity of the flame. The hydrogen for the flame comes from this cylinder here.
We're about halfway through.
Before beginning the separation, the operator must set the flow rate of the gases and the temperature of the oven. The temperature of the inlet port is also set at a level that ensures that the sample is fully vaporized, and the flame ionization detector must be lit. Here, we will separate a mixture of methanol and methyl benzene. About 0.1 microliters is taken up in a hypodermic syringe. It is then injected into the inlet port through a self-sealing rubber disc called a septum. The first piece is methanol, the more volatile component. Its retention time, that is the time taken for it to pass through the column, is about 1 minute. The second
Notice it's also the lower molecular weight.
5 minutes is the less volatile methyl benzene. Its peak has a larger area, showing that there is more of it in the mixture. The computer calculates accurate retention times and peak areas.
At one time, people used to actually have to interpret those charts and figure out what these compounds were. But now it's all done by computer, including the measurement of the area underneath those curves.
The computer calculates this. This instrument is used for undergraduate practical sessions, and samples are run singly as and when each student is ready. In this alternative instrument, the gas chromatograph is on the left, and the detector is a mass spectrometer, which runs the mass spectrum of each component as it comes out of the column. This can be particularly useful when analysing an unknown mixture, as the mass spectrum can help to identify each component. The combined technique is called gas chromatography mass spectrometry, GCMS. This GCMS instrument has an auto-changer for the samples. Many samples can be loaded up and run automatically, perhaps overnight.
Okay, thanks for staying a little bit later and tolerating this. Let me get the instruments back, and if you could, maybe one or two, you could like grab some of this and just drop it by that back door on the opposite end of the hallway here, all the way at the opposite end. Yes. Actually, I think did I give you numbers in there?
Yeah. Well, the full rate.
Yeah. Oh, okay. And you got the did I give you the 20 readings? Oh, yeah, there they are. I couldn't see them there. It's too small for you. Because I kept doing that. You're younger, you can see stuff like that.
Well, I don't understand this part is for 20 readings.
No, what happens is that when you're working 11, hey guys, if you could grab, if I could get some of you to grab some of this for me. Oh. Yeah, just pick that up and drag it to the opposite end. Anything you see here. Everything you see here.
I drag it to the end of the hallway?
Yeah, the opposite door,
Yeah.
all the way to the other end, the locked door.
Alright,
Oh, where'd you go? Hang on a second.
Yeah, I'm gonna bring it.
Okay, good, thank you.
so we don't need to do this, right? Do we need to do this?
No, I gave you the top part here. What I did on that is I gave you 1, 9, 3, 2, something like that.
Oh, you did?
Yeah, I think so.
Oh,
Well,
on
my
the
phone
Excel
has it,
sheet,
you can
right?
show her.
Yeah.
Oh, okay.
You can show her my phone.
Okay. Oh, yeah. Oh, I still have your phone here. Okay. I know you had to come back.
Oh, okay.
Yeah. So let me tell you what this is.
Okay.
A person that's analyzing that filter, that little pie-shaped wedge, they're going to take a look at that little circle. They're going to count how many fibers, and they counted 2. Then they're going to move it. Oh, they counted 3. Then they're going to move it. None. They're going to move it. They're going to do that 20 times, a minimum of 20 times, or they'll stop at 100 because then it's really high if they got to 100. Right? So they do that 20 times, and then they take those 20 readings and they average them. So that tells them that the average number per circle is 2, let's say, right? And then they figure out, well, this is the area of the filter, and this is the tiny area of those circle, and there's 5,000 of those little circles in that filter. So each one of them has an average of 2.
Right.
Then you can say 2 times gives you the number of fibers.
Okay.
And then if you know how much air that you pull through, right, you can say, well, there's 10,000 fibers in 20 liters of air. And then 20 liters of air is the same thing as 20,000 cubic centimeters. So you can say there's 10,000 fibers in 20,000 cubic centimeters. So that means there's half a fiber per centimeter.
Okay.
Cubic centimeter.
So basically using these fields, we answer these questions on the bottom.
Yes.
Okay.
Okay. And if
And
you
then-
get it wrong this first time around, I'm going to go through these calculations in not specifically the same numbers you're working with,
Yeah.
but I'll go through them again like I did with the other thing
And this
for when I start next week.
Okay.
is where we write the report.
It's online on
It's online.
Blackboard.
And that's
It's in the it's with the material that's on the lab assignment.
And this is what we write our